Okay, let's get started. Thank you everyone for being here. It is my great pleasure to welcome Mark Guzdial to CMU. I've had an academic crush on Mark. I don't know, 8 years or so. So I'm really excited to have you here. Really, you, Josh, I've been. You probably have no idea that I had this crush on you, and I've just experienced completely in the form of reading your papers and following you on Google Scholar without you knowing that I was following you on Google Scholar. So Mark is here today primarily, I think, to talk about a new program he's running, which is called the PCAS, right? The Program in Computing for the Arts and Sciences. Is that right? That's right. Which is a brand new program at the University of Michigan. He's a professor at the University of Michigan in electrical engineering and computer science. And he's here to talk mostly about CS education, which is something we should all think a lot more about. Thank you, Mark.
Thank you so much, Josh. I appreciate it. Thank you all for having it. This is so nice to have such a whole bunch of people. I mean, it's a crazy time of the semester. So I want to express my appreciation. I want to start out, actually, I am going to talk about PCAS, but I want to sort of sneak up on it. I'm going to give you a framing that's really important to me and why I'm doing what I'm doing. This is C.P. Snow's The Two Cultures in the Scientific Revolution. Occasionally, I'm going to do a poll of the audience. I know you're all eating, but we're going to try this anyway. Could I have everybody right now hum? Great. Okay. If you've ever read this book, please hum. Okay, that gives us a sense, right? Without having to show your hands, we got a sense of how many people. Okay, so my advisor made everybody in his group read this book, C.P. Snow's The Two Cultures. C.P. Snow was a scientific advisor to the UK government during World War II, and he wrote this book because he saw that there was a split in the Western culture between the people who care about the humanities and the people who care about what we would now consider to be STEM. That he saw decisions being made during World War II, which were being made for purely technical reasons without thinking about all the humanities aspects, or decisions that were being made entirely humanities and didn't really understand the science behind it. C.P. Snow blamed the humanities for this. He said that they consider science as yet another way of coming to know, as opposed to one that's particularly privileged by evidence. Eliot made all of his students read this book because he wanted us to think about who needs what we have to offer in terms of computing education, but isn't even going to come into the room because they're on the other side of the schism. Okay, so here's the story that I want to tell you about. Computing was originally created to be taught to everyone. I'm going to make a historical argument, one that's actually really near and dear to what you all do here. But computer science has become more narrow. And I want to talk about who do we reach with computing education today, which you're already pretty aware of what that is, but we'll put the numbers on it. And then ask the question, if you're going to teach computing to everybody, what should we teach to everyone and how? And then I'll finally get to this argument that's the title of my slides. How do we broaden participation in computing by moving outside of computer science? Okay, if you know who this is, hum now. This is George Forsyth. He was a mathematician at Stanford. He's the first person to publish the term computer science in 1961 in the Journal of Engineering Education. He was describing what he thought everybody ought to learn. He particularly made the argument in 1968 that the computer is a necessary tool for learning science, mathematics, or engineering. The argument that he was the very first one was actually made by Donald Knuth, who wrote a history that included him. I want to pick up the story in 1961. There was this amazing seminar at MIT, at the Sloan School, Computers in the World of the Future. It was held in 1961. Who was there was like a who's who of computing in 1960. We're talking Gene Amdahl, John McCarthy, Alan Newell, Herb Simon, Grace Hopper. This book by Greenberger came out in 62, way out of print. I'm literally scanning my used book copy of this for these slides. Where it's the transcripts of all the lectures and the transcripts of all the discussants' comments. It's pretty amazing. So one of the talks was by C.P. Snow, the author of The Two Cultures. You may recognize that one of his discussants is Norbert Wiener, the father of cybernetics. So C.P. Snow made the argument in this piece that absolutely everybody ought to learn computer science. And the reason why they ought to learn computer science, amazingly prescient, He saw in 1961 that computers were going to rule everything. And if you don't understand how computers work, you don't even know how to ask the right questions. So how does this adjustable rate mortgage work? How are you computing my credit score? A particular quote, you'll excuse me, I'll actually read it to you. A handful of people having no relation to the will of society, having no communication with the rest of society, will be taking decisions in secret which are going to affect our lives in the deepest sense. 1961, that was pretty amazing that he saw that. This slide was given to me by Michael Casperson, who said, Peter Naur was saying the same sorts of things. Okay, and as you can all see from the Dutch, Michael gave me a translation of it. I'm just going to read part of it to you. This must be regarded as perhaps the most important reason for promoting the understanding of informatics. This is a necessary condition for humankind's supremacy over computers and for ensuring that their use do not become a matter for a small group of experts, but become a usual democratic matter. And thus the democratic system will lie where it should with all of us. Okay, I now want to go back to that computers in the world of the future. One of the other chapters that made the same argument that everybody should learn about computing was by your own Alan J. Perlis. Perlis argued that, this is great to be in the one place where I don't have to explain who Alan Perlis is. So Perlis argued that everybody should learn computing because of the experiences that they were having in 61 teaching computing. So for example, the business or management, I don't remember what it was called at the time, department was actually teaching how to build economic simulations. In general, economics is not, at least at that time, an experimental science. Let's devalue the dollar tomorrow just to see what happens. But you could build simulations. And through simulations, you could come to a completely new understanding. So he was really prescient in thinking about the development of computational science and engineering. He argued that everybody should learn to program because learning to program changes everything. It changes how you learn everything else. So programming changes how we come to understand. So Perlis, with Herb Simon and Alan Newell, published the first definition of computer science. One that I think you all are familiar with. I think it still appears on your web pages somewhere. This is the definition, which was sort of at the heart of computer science here, the study of computers and all the phenomena surrounding them. I'm going to make the argument that this is not how most people define computer science today. I'm going to call this computing, just to make a distinction. Here are some of the definitions of computer science that I found. The first one, I found a New Maryland CS. I'm going to give them credit, though the one that's on Wikipedia is pretty much the same, and I can't really tell you which one came first. Computer science is the study of computers and computational systems. This one is important because it's actually the definition for the whole K through 12 CS framework, which informs the Computer Science Teachers Association and most of our states' computer science standards, if they have computer science standards. Computer science is the study of computers and algorithmic processes. And the final one, this is the ACM IEEE definition, which underscores the computer science undergraduate program. You can read these, but all I really want you to take away is the most significant bit. This is very different than the other one. In particular, these are much more narrow. This is not, and the study of all the phenomena around them. Okay, so I'm going to now fast forward a few dozen years. In 2016, President Obama announced his CS for All initiative, which continues to this day. Okay, this lag is a little bit. Computer science is a new basic skill necessary for economic opportunity and social mobility. And I want to ask the question, when did this become about economic opportunity? I mean, of course it is, right? Getting into a CS major means 6-digit opening salary when you graduate, right? For a lot of people, this is changing lives. This is changing your family's life. This is a really big deal. I do not want to diminish the importance of the economic opportunity. But if you think about it, Forsyth, Perlis, Snow, Naur, and Simon, Newell were all arguing about computing education decades before Silicon Valley. So what was it that they were arguing for? They weren't arguing for preparing students for software development jobs. What was the goal of computing education back then? What's the delta between those 2 points that we might be missing today? So who gets access to these powerful ideas? Who gets computing education today? I'm going to mostly focus at the high school. You all know who's in your undergraduate programs, and you're probably pretty familiar with what's going on in undergraduate computer science general. Justin Reich wrote this terrific book, came out during the pandemic, Failure to Disrupt, why technology alone can't transform education. He had one statistic, which in hindsight is like, well, it's actually pretty obvious, but it really impressed me. What is the average number of Scratch projects written by each of the 59 plus million Scratch programmers? Well, it's actually pretty easy. What's that? One? No, it's less than one. It has to be. Okay, there's not 59 million projects out there, right? So it's less than 59 million. So it's kind of disheartening when you think about how much participation there actually is in computer science. So that's what this number is. This is the percentage of US high school students that ever take a course in computer science. Okay, and this is as of, this is 2022 numbers. This is data from it's code.org, CSTA, and ESEP, the Expanded Computing Education Pathways Alliance. For people who don't know, the US education system is distributed. It's a states' rights issues. Each individual state decides its own K through 12 education system. So if you actually know what's going on in the state, you have to look at the state. So Texas actually has a wonderful dashboard that lets you, one of the reasons why I like their dashboard is they don't just tell you now, they let you look at the historical trends, right? So this is the participation in computer science by gender in Texas. Overall, only 4.4% of all high school students took CS courses, and they're already getting ready for the next question. Well, how many schools actually offer computer science? Well, 5.6% of students at schools offering CS took a CS course. This is a really low number, folks. And here's the really interesting, I was actually had a wonderful lunch and we talked about exactly this part. Continue the line. When do we get to 50%? When do we get to 100%? I realized a while back, I'm not going to see 100% of high school students in the US taking computer science in my lifetime, right? And then if we look by race, it's similarly awful. Okay. So to a first approximation, there is no computer science in US high schools, right? If over 90% of the students never take a CS class, how much computer science is really there? Now that's not fair. That's not fair to huge amount of efforts, huge amount of teachers who are doing it. But who is in the computer science classes that exist? This is not a very pretty slide because I just didn't have time. Barbara Erickson, who, full disclosure, is my wife, generates this every year. And it turns out to be really hard to get now because the College Board has locked down their data. And she happens to be on the small list of people who actually get the College Board's data each year. This is essentially every advanced placement exam. And the size of the dot is how many people take that exam. And the position on this graph is, this is females equals males exam takers. You see the vast majority of AP exams are female majority. You may now look for computer science. Let me show it to you. There in the corner. Right? One more fact that's going to try to drive you crazy, that drives me crazy. This is a log scale. We in computer science hope to one day be as female dominant as physics. So it is an incredibly skewed graph. So this really informs what I do. If we want to teach computer science for all, we have to teach where the all are, and that's not in computer science classes. Now, maybe that's related to the definition of what computer science has been. I couldn't tell you how it all has happened. But I can talk to you about why the focuses that I have. This is not the most recent data. This is 2019 data, but close enough. The stats are about the same. US history versus computer science principles. Computer science principles is far more than gender balanced than computer science A. AP CS principles is less than 30% female. AP US history is over 50% female. AP US history has 6 times more Black students than AP CS principles and 14 times more Hispanic exam takers than AP CSP. And I use Black and Hispanic because those are the actual terms used by the College Board. So I don't want to change the definition of how they collected their data. Okay, yeah.
If you go back to the slides, biology is pretty high up.
Yep.
Why? So this isn't really a question of science versus humanities.
I don't think it is. Yeah, I think this is one of the interesting responses to the argument that says if we want more women in computer science, we should have more female faculty. There are many biology departments that are all male, and yet they all tend to be female dominated in terms of these students. So what actually influences these things? More complicated. Great question, thank you. All right, so if we were to teach everybody, what is in that delta between the 1960s and 2016? So the first name that people are going to think about when they think about teaching computing to everybody is probably Seymour Papert, pictured in the upper left. Papert invented the logo turtle, the little robot device, which is now just a thing on your screen, which has relative graphics systems. The picture on the right was given to me by Gary Stager. He's on the right-hand side. The person in the middle is Cynthia Solomon, who developed all the logo curriculum with Seymour Papert. The person on the left is, well, I'm blanking. Oh, shoot. Suddenly the name just went away from me. Wally Ferzig. Thank you. Wally Ferzig is the actual inventor of logo. Seymour was a consultant on the project. Seymour claimed that children can learn to program, and learning to program can affect that they work with the way they learn everything else. So what are the kids doing with logo? So logo is from the Greek word logos for word. And in his 1968 report to the National Science Foundation on what kids are doing, this is one of the first programs that students write. They randomly pick a noun, randomly pick a verb, randomly pick an adjective, and then generate random sentences with it. No mathematics. There's no turtle graphics. I mean, turtle graphics is how people think about logo today. But when it started out, it was about words and about saying things and about expression. I love this paper that came out in 2017, Katie Rich and Company, Diana Franklin's group, asked the question, what's the starting place for K through 8 CS learners? If you're going to start kids on a learning trajectory, what's the very first things that they need to learn and what comes next and what comes next? And so they built these really cool learning trajectories. Mathematics does this very often. Science education does this very often. I want to look at the left-hand side. I'm going to type out some of those things for you. Precision and completeness are important when writing instructions in advance. Different set of instructions can produce the same outcome. Programs are made by assembling instructions from a limited set, and you can read the rest. I'm going to bet that all of you would say, yes, of course, you have to know all of these things to move on in computer science. But I'll bet you're also thinking, and this is learned in prox the first 30 seconds of using computer science. I think there's a lot of evidence that it's not. That these are actually fairly hard concepts that most people don't have. And in fact, I'm going to argue, you don't even need all of these. Scratch doesn't. There have been a lot of really fascinating studies of what's going on inside us. What are kids producing with Scratch? One of my favorites is by Yasmin Kapai and Debbie Fields, looked at thousands and thousands of kids' Scratch programs. Most Scratch projects are just stories. They use forever loops, no while, no repeat, no for. No Booleans at all. Rarely do you have variables. It's just movement and sequence. But Scratch is likely the most used programming language in the world. There is expressive power and even a subset of computer science. Powerful, things that you can really do interesting things with. I have my academic crush on the Bootstrap group. I think that they do just amazing stuff. I am so impressed by the data they've gathered, which really shows that using Bootstrap leads to improvements in algebra learning in the Bootstrap curriculum. And so this is from one of their early papers, 2015. This is the column that I want you to look at for right now. Those are the programming concepts needed to do Bootstrap, where kids are building video games as a way of learning algebra. They don't ever code repetition. Okay, it's functional. It just has a behind the scenes loop. So there's a lot more math, but the point is that there's learning power in even a subset of computer science. So we don't have to cover all of computer science, and a lot of really useful stuff in that space between George Forsyth and President Obama. All right. How would we change computing education to reach everyone? I want to argue that actually changing computing education will likely involve changing computing. Okay, the hum test again. If you know what this is, please hum now. Just a couple folks. This is a screenshot of the first desktop user interface. This is Smalltalk in the mid-1970s. It was the first time that we had multiple windows, overlapping windows, icons, menus, mouse pointer, multiple fonts and styles. Smalltalk was invented at Xerox PARC in order to realize Alan Kay's goals for computing education. So working with Adele Goldberg, and most of Smalltalk was built by Dan Ingalls. These three people changed the way that we use computing today. I mean, with their whole group, but these were the three leaders of that group. In order to realize a vision of computing education, they changed computing to make a computing education vision work. Okay. Crud. Hopefully nobody saw that. Okay, if you already know, because you've seen one of my blogs or talk, don't answer. Someone else, tell me what this is. Oh, I like Kelly. Thank you very much for squinting. That made it very clear that we're okay. Yeah, shoot.
Is it a keyboard?
It is a keyboard, but what does the thing do? There's paper tape. There is indeed.
Drawing machine?
Drawing machine. Oh, that's a wonderful thought. It's not, but it's a good thought. Yeah. Oh, what a cool idea. No, that's not what it is. Yeah.
Wait, Turing machine.
It is not a Turing machine. It's a printing telegraph machine. Telegraph comes in, prints onto the piece of paper. Okay. It's a pretty brilliant idea. To generate a letter, I'm going to type a key. The first printing telegraphs were invented in 1840. QWERTY was patented in 1868. For almost 30 years, if you had this brilliant idea, what if you generate a letter when you press a key? Well, that's your keyboard, folks. It's the only keyboard you have. We don't have typewriters yet. Right? So here's this powerful idea. Maybe we're still waiting for our QWERTY keyboards. Maybe we're looking still for what's going to make the great ideas of computing accessible. So in my work, in my group, we've been focusing on what we call task-specific programming languages. And then it totally was an accident. TSP languages. Oh, they're teaspoon languages. We put a teaspoon of computing into other subjects. Our goal is to integrate programming to enhance learning in high school and university non-CS classes where the students are, where the diverse students are. We use participatory design with teachers to result in adoptable programming, things that the teachers might actually adopt. And then we build them to be highly usable by, there's no tech, very rarely is there a text editor. You are mostly just put into an user interface that is specific to the particular task. So we put a teaspoon of computing in other subjects. So here's the first one that we built. This is DV4L, Data Visualization for Learning. It's a collaboration with Tammy Schreiner, who is a history professor at Grand Valley State. She's a social studies education researcher. She's shown that by going through all of the standards for 50 states and Washington, D.C. and Puerto Rico, that they all require social studies to cover data visualizations and to teach how to understand them. The obvious ones, timelines and maps. Of course, how do you have a history class without talking about timelines and maps? But also scatter plots, charts, tables. But she finds that a very small percentage of teachers actually teach that. Her explanation, she's probably sick of hearing me quote her quote back to her, but she says, you don't become a US history teacher because you love numbers, data, and computers. So how do you convince them to do this? So one of the things that makes DV4L different is that the driving question is in the upper left-hand corner. As soon as you get started, you specify why you're doing it. Now, most project-based learning, inquiry-based learning in the United States is driven by driving questions. It's part of the literature. That's how you keep students on task. We built it into the tool because the teacher said, well, it's not inquiry unless you put a question there. So we built it into the tool. We always generate two graphs. There is a whole field of historical thinking. I had no idea until I got started with this. And one of the arguments is you don't have an interesting history problem until you have two data sets, two accounts, two stories that don't agree. So we always show two visualizations, which already, right, how many Tableau, CodeApp, whatever else you actually have you build two at once. For our teachers, that's a necessity. You have to, or it's not interesting. And then we create a space where you can save all of your inquiry. So it's all about multiple visualizations. If you were to hover over one of the ones on the right, you're going to say, like, what the heck is that thing on the right now? I've forgotten. You hover over it, and I'm going to show you a JSON of how you specify that graph. JSON, Guzdial, why are you doing that? Because when we started out showing people things in JavaScript and in Vega Lite, the teachers liked Vega Lite. All right. For those of us who program, they're like, you're going to have people type, oh, sorry, you can't see it. You're going to have people type curly braces and quotes. It's like, doesn't matter. They can read it. That's what they care about. So we then create this new space that you click on the customize button, where I'm going to give you the two graphs and I'm going to give you the JSON, which you now just don't see. You can edit. And if you edit it, I'll change the pull down menus for you. And if you change the pull down menus, I'll change the code. And both of these will change the graphs. This is a way of easing people into the coding with a highly scaffoldable multiple link representations. when Bahari Namipur, PhD student working with me, tried these out with teachers. We actually had some adopters. Middle school teachers hate this. High school teachers love this, right? So it's actually really important to understand. When I first got started, I was like, oh, this will work from middle school to high school. You know the difference between a 12-year-old and 18-year-old? It's really enormous. It's really hard to build something that'll work in both. So what is it that our teachers face when first dealing with this? Again, social studies teachers, history teachers, the first time they see something with programming, they've never seen an intermediate representation, right? They've never seen HTML. The idea that you type something here, which gets transmogrified by the computer into a different output, that's a completely new idea for them. The second one is that sometimes when you specify a notation, you're going to specify it wrong. And that's when debugging starts. Again, it's not something you dealt with Excel, PowerPoint, and Word. Something doesn't work, you just fix it right there, but you're fixing the thing as opposed to fix the notation, which is then going to generate it later. And I can now tell you from our work in PCAS, our students are having the same problems. Tamara Nelson Fromm is spending a lot of time with the teachers. Let me show you one more teaspoon language that's going to show up again later. This one's called Pixel Equations. We designed it for an engineering course in a Detroit Public High School. They were trying to adopt a robotics curriculum from the University of Michigan. One of the tasks they were going to do is gather data from robotic sensors and then visualize those data. We interviewed undergraduates to say what was hard about this task at the university level. And then of those things that they found hard, the math teachers told us, these are the ones we want you to focus on. So the first one is that equations that describe sections of a graph can also describe sections of a picture. So in DV4L, you specify what your input picture is, you specify part of the graph you want to specify, how you want to change the red, green, or blue, click run equations, and then I'm going to change the picture the way you specified. The second is that colors can be specified by equations. They never thought about a numeric representation, which would generate pictures, and that we even use equations like double the green when y is less than 200. And finally, that we can select pixels not by using just coordinates, but by specifying something about the pixels themselves. If the blue is greater than 200, then half the blue. One of the things that's also in here, I'm not going to demonstrate, but all of the red, green, and blue can also be azul, verde, and rojo. Because if you're inventing your own programming languages, why not just do English? How about avoiding the English hegemony? So basically, Pixel Equations is really building image filters. It really is programming, but there's no curly braces, no for loops, no ifs, no assignments. You're just specifying the various pieces. Let's get that. The various pieces of the image filter that matter for math and engineering. We just had a piece published in the communications of the ACM where we specify our definition of a teaspoon language. Teaspoon language first is they can be used by students for a task that is useful to a teacher. When I showed the draft of this to Sriram Krishnamurthy, he says, no, number two, they are programming languages. That has to be number one. It's like, no, the first most important thing is it solves a problem a teacher cares about, a non-CS teacher, because otherwise it's just not interesting. And then the third one is actually really important. It can be completely learned in less than 10 minutes. You all totally know these two teaspoon languages. There's nothing else in what I showed you. That's it. Right? There's no APIs, there's no libraries, there's nothing else to them. So if you can completely learn them in less than 10 minutes, you can use it in one class period and then throw it away and it's okay. Right? You don't have to amortize the cost. Okay. So what we're trying at Michigan, all of this up to now, I actually have some data on. The rest of this is just leaping into what I'm spending all of my time in now. And now we're going to change the slides because we're no longer in computer science land. I now teach in the College of Literature, Science, and the Arts, which is 30,000 of the 50,000 students at Michigan. At one point, I was given a list of all the faculty in order to send them a survey. There are over 2,000 rows in that spreadsheet. LSA is just enormous. And so I am directing the program in computing for the arts and sciences. So that link goes to the webpage. So we're creating a new program for LSA that has no connection to computer science and engineering and no connection to the school information. Here's the 3 key points that I hope that you're going to take away as we go through this. How we did the self-study. How do we answer the question, what do LSA students need in computing education? What do we currently offer at Michigan? The second part is, how do I design these two courses that I'm going to describe to you in a minute? And the third is the scaffolded series of computing activities. I am probably now the largest adopter of Teaspoon languages. Okay, so in September of 2020, the University of Michigan College of LSA invited Gus Everard and I'll talk more about Gus in a minute, to convene a task force to ask the question, what does LSA need in computing education? What do students need? But mostly, you can't ask students, in English. So what would you like to know about computer science? So we mostly interviewed faculty. We also did a lot of looking at what programs and courses currently exist. Gus studied hundreds of courses. And this is where you can get the final report, which I'm very proud of. It is really interesting read. I did not write most of it. This is a little bit of, it's not just a humble brag. It's really interesting to look at because we did a bunch of peer studies. We had lots of interviews, lots of quotes. This is probably the biggest takeaway for me from what we did. We came up with 3 themes for what computing education means in the liberal arts and sciences that are different from computer science and information. The first is computing for discovery, that computational science exists. Neither CS nor information at Michigan teach computational scientists how to do computational science. We don't teach the natural scientists how to do this. I think this is really interesting because this is what Alan Perlis was arguing for. Computing for discovery is really critical for what we do with computing. The second one is computing for expression. As you all know, from texting and social media to AR, VR, and Pixar, computing has changed how we express. And that's what Seymour was exploring with Logo when having kids generate language. And the third one is what CP Snow and Peter Naur were telling us, that we need to think about computing for justice, that we have to be critical about our computing systems and ask, where are we exacerbating inequities and how do we make things better? Oops. Some of the findings from the task force. There's only 3 computer science courses, which cover about 50% of everybody in LSA. They're in statistics and computer science, 2 in computer science, 1 in statistics. Only 20% of all LSA students, so about 30,000 students, only 20% ever take a second course. Most LSA courses, as you would imagine, ones that are in LSA are in discovery. The natural sciences has a bunch of these, some of the social sciences. The computing intensive courses in expressive and justice are electives. Very few people ever take them. The faculty, there's tons of great quotes in the report. I'll just read to you this one excuse. I think our goal should be for LSA students to receive more of their computing education within LSA with a liberal arts basic science perspective. To me, this means not just writing code, but interpreting, critiquing the products of the computation. And when we looked at all of our peer institutions, we couldn't find an institution that was doing all 3 of these, all of the liberal arts and sciences. So we're trying to create PCAS. We just launched in summer of 2022. It's me and Gus Everard. Gus refers to himself as a first-generation computational cosmologist. He simulates the Big Bang. He's a physicist. So we have 3 big goals: to meet the needs, to meet the needs of all LSA students. We can't say we're meeting all the needs, but so for every LSA student, no matter what their program is, you probably need some computing. Let's help you get there. We're going to create new courses. We're going to create new programs and credentials. So I currently have 2 classes. I love the course code they assigned us. We're not CS. There was a lot of negotiation, a lot of policy. We're Comp 4, computing for. All of our courses are about computing for something in LSA. These are the 2 courses that I've spent all of my time this year building and teaching at the same time. Relatively small. Justice was like 11, 14 students. Computing for creative expression was 9 students in the fall and 39 students in the winter. I hope we don't keep quadrupling. In fall 2023, Gus has led, I'm so proud of this class. Gus has led the lead on this. Some of the natural sciences are already teaching Intro to Python. He was able to get 5 departments to come to the table and say, could we define one? Because not all the natural sciences have it. Not everybody has the spare teaching capacity to teach an Intro to Python, but everybody could use it, couldn't they? Let's build one. And so that's what's going to be started taught in the fall. And then Gus is teaching a class that he promises will be welcome to humanities students, the transistor disruption, how a tiny tool transforms society and science. Okay, so this was my big question last summer. It's not like I can look up the expression and justice classes in the IEEE ACM computing curriculum and say, oh, here are my standards. So I, again, like with the Teaspoon languages, launched a participatory design process. I formed advisory groups of faculty who self-identified, I care about computing for justice, I care about computing for expression. And I sat down with them with shared whiteboards, Padlets. One of them was about learning objectives. These were learning objectives that were in our task force report. Somebody had said people should know this. And then some activities that could be associated with it. The instructions to them, it's one shared whiteboard, but we're getting the transcript, so we're getting the rationale. Move to the right, things you think are important. Move to the left, the things that you don't think are important. So here, for example, is justice. I was kind of shocked. Everybody that I've talked to in critical computing says, of course, that the most important thing they want other students to know is that a database is used to generate HTML pages pass-through template. It was amazing to me. That is the number one thing. I teach that, right? I teach it with blocks. And so you can see some of the other ones. I want to point out, here are the ones that we as computer scientists highly value, and they've been moved pretty far to the left. Here is expression. Here's that write secure, safe, robust code again, too. These two screens are my standards. I spend a lot of time going over these, going over the transcript, trying to figure out what is it that I should be teaching. I don't hit all my standards, like almost nobody hits all the standards for quick. I don't hit all of these, but this is what I try to do. The common learning goals for the course, in both of these courses, we want students to become conversational programmers. These are people who don't want to become professional software developers, but they want to be able to talk with them. And so this term, conversational programmers, Philip Guo and his group first came up with it. All of my faculty said, yes, I want my students to be conversational programmers. They want them to develop self-efficacy, the belief that they could learn more in programming should they choose to, and then specifically to use programming to explore a set of concepts, not for its own sake. And one of the things that I heard over and over again, please don't scare them off, and they don't want math. All right, so let me tell you a little bit about how we scaffold learning to program in these Comp4 classes. We start out with teaspoon languages. We use pixel equations in the expression class. We use a different teaspoon language for helping students to recognize sentence parts. Chatbots came up a lot, and this is last summer. This is before ChatGPT. They said, I want my students to be able to build chatbots. So we do it via production rules, not via machine learning. And I want them to understand how and I'm trying to figure out, how do I help these people to understand that you can match words to types and that you could generate things by types? So we built this little tiny, so that thing right there, that's your whole program. That's your model of a sentence. So noun, verb, noun, adverb recognizes the lazy dog runs to the student quickly, runs to the professor, to the tree quickly. But if you say house, it's not going to recognize those last two. Well, why? Because house isn't up there, which is already by itself an important idea for these students, that the execution of a program depends on both the algorithm and the data. Right? They've never seen that before. So the fact that this, even as simple it is, can lead to debugging issues. And then we work with generating sentences, is the flip side of it, with different kinds of sentence models so that we can say, do you want more parts to your model to generate better sentences, or do you want more things in the dictionary? What's the trade-off there? In both these teaspoon languages, we can still do actual activities. So like I'll give them negation in pixel equation and then say, so what if the number is other than 255? What do you get? Go explore. In the justice class, I give them language sentences that I took from various websites on Spanglish, African-American vernacular English, and Hawaiian Creole, and say, okay, can you build a sentence model that recognizes both? Put anything you want in the dictionary. And you realize, well, that's not hard. Lunch is also a noun, but a stoy, do I want to call that a noun or a verb? How do I make that work? That's what I want them to think about. They do most of their programming in Snap. I am a huge Snap fan. It is absolutely amazing. Yes, it looks like Scratch. It's basically Scheme with a ton of multimedia extensions. So after they do the pixel equations, they build image filters using things that look like this. So these are all custom blocks. I can build my own blocks. I can build my own control structures. When we talk about chatbots and recognizing sentences and words, we talk about a little tiny simple algorithm. Imagine there are the yellow and the green party, and your Twitter bot says something negative about the yellow group, and you wait for somebody to say something bad about the green group. And then you take that same green noun and you say something positive about it. A reasonable algorithm to think about how Twitter bots might work. And then we also do some data science stuff, like looking at all the first names of the men who are on the Titanic. And then at the end of 4 points in expression and 5 points in justice, I give them an ebook to do. almost the ebooks, this is Barbara Erickson's area of expertise, where I say, here's a snap program you've seen before. Here's a Python program that does the same thing. Answer these multiple choice questions about the Python program. I'm not going to teach you Python, but I'm going to show you that there's transfer. That the things you've learned about snap also work when you get to Python. Just to give you, I'm not going to go through all of this, but I'll give you a sense of what's in the justice class. So the first assignment is build a haiku generator. So they can think about what does it mean to generate reasonable speech randomly. We talk about how the internet works. We do a lot of, I told you, I really do talk about how do you generate web pages from other things, from blocks, from Twine, from databases. We talk about how search engine works. We do visualization using CodeApp. We talk about AI and ML. How could you not talk about AI and ML in the course on computing for justice today? And then talk about limitations of technology. In the expression class, I love teaching this class. It's so much fun. It sounds actually a lot like the course that Tom Cortina teaches. We talked this morning. So the first task is build art from shapes. This one on the upper right-hand corner is by a student. This is his first program he's ever written. We do how image filters work. They have to build their own image filters. They manipulate digital sounds. We talk about building oral scenes. Tom was saying they talk about doing sound stories. This is from individual pieces of sounds. I'm sure that you can figure out where it's supposed to be. And so this is by splicing sounds, changing the frequencies. The sound of the train departing the station is the sound that plays backwards. So the train came in with one sound, it reverses, going back out. We built chatbots. It all leads up to them building a set. Oh, I love this one too. They have to build a drawing program where they must use either the microphone or the camera as one of the inputs. So when they're working on that in lab, you see people like trying to move their cursor like this, or trying to change colors or line widths or something like that. Okay, my open research questions. There's a lot of them. Are we getting there? Are we giving arts and humanities students what they want, what faculty want them to get? We're really fascinated by the process. We don't teach a software engineering process, but they're clearly developing a process. One of the things Tamara Nelson Fromm is studying these students a lot. They do a lot of things by bricolage. I'm going to try this. Oh, that didn't really work. What about, but that's, oh, this is a neat state. I'm going to try this direction. And those aren't failure states. Those are, I learned something and I realized what's hard to go the next step. I'm not going to go that way. And they end up learning a lot by exploring this. The big question that everybody who's looked at computing education or cognitive science and computer science are wondering, so what's the load? You're using 3 languages in the same course? Yeah, I don't know yet, but it seems to work. I'm going to show you a picture of something that happened this last semester that just like was so amazing to me. So I see Teaspoon languages, Snap, Python as a progression. It's a scaffolded structure. So I've taught everybody with Teaspoon languages, 1 class period only. Next class, or sometime later, they're doing their lab where they're working on building their own image filters in Snap. And I took this picture. That's pixel equations on the screen. Some of the students started going back to pixel equations to try out ideas and then encode them in Snap. If you worry about transfer, this is a pretty shocking evidence of transfer, them to choose to go back to the earlier level in order to bring it forward in order to do their image filter. Here are some of the research questions we're not exploring. And I can't explore these. I live in the College of Literature, Science, and the Arts. I cannot be about recruiting students into CS or information. I am about making them successful in their chosen fields, but with computing. So here's my summary. The founders of computing proposed programming as a tool for learning for everyone and for learning everything. But somewhere along the line, it narrowed into getting jobs. Nothing against that, that's fine, but there's a delta. There's something left on the table. How do we get to that? It's easier to argue that no one is getting computing in the United States in high school than everyone is. And I think the computing education for everyone is both broader and smaller than for software development. And maybe we just need a teaspoon. And then what I'm about is trying to figure out how do we teach computing for everyone by focusing on arts and humanities and scientists too, but Gus gets most of those. And at Michigan, we're developing PCAS, or liberal arts and sciences. So I have lots of great collaborators on this work. And thank you very much for your time. This is the question portion. Yeah.
So you live in the ECS department. What do your colleagues think about this?
Mostly don't know. If anybody's listening and they now do. No, computer science, like many, particularly state universities, computer science departments, is completely overrun with students. University of Michigan Computer Science program is explicitly capping. This fall will be the first time that students, if they apply to go into computer science, will be vetted. And some will be admitted to the University of Michigan, but not computer science, and you may only be vetted once. Those students may never get a computer science degree at the University of Michigan. They're going to create most of the slots for people who are already on campus who take a computing course, but they're trying to reduce by 30%, which is a big loss. So Mike Wellman, my chair, who's been amazingly supportive in computer science, said to me when he signed the MOU, signing me off to LSA for 3 years, I have a split appointment, 50%. My tenure home stays in computer science, 50% LSA, but LSA has bought me out of all my teaching. So other than keeping my students, keeping my service load, I'm an LSA faculty member. Computer science can't get involved in helping develop a non-majors program when they're capping their CS enrollment, because it doesn't work. So I'm mostly on my own. PCAS in general, even LSA has not said that much about it, because part of it is, as some of the discussions I had this morning, the definition of what we're going to do has changed so much just since July 1st. We're constantly trying to figure out, how is this going to work? When I first got started, they said, go create majors right away. So we'll have majors for the computer science people who don't get into computer science to switch into. And then a few months later said, stop trying to create majors. You're really upsetting the humanities people who want to talk these through things later. And then realize, I'm going to phrase it my way, not the way that the deans phrase it. If there was a major in a humanities subject, say English, and a computing plus that subject, computational English, are you more likely to grab students from computer science or from English? That's a real problem. They don't want me to cannibalize the humanities, and I don't want to either. So what we'll likely do is create minors that someone taking a major in the humanities might take a minor to indicate their computational component of what they know. But, and that decision that I just offered you has only been made in the last month. So we haven't said that much about PCAS because we're still figuring it out. So much, yes.
So just following that last thought, who would own computational English? Would it be English or computer science?
Well, certainly not computer science. They literally don't have they're not a player in the game. PCAS has no tenure track faculty, so it would probably be owned by English, but that's not currently on the table. Currently what's on the table, if English wanted to do a computational English degree, I will help them. There is actually talk about trying to do computational biology with PCAS helping, something you all have because you got a great definition for computing. Yeah, I don't know.
I mean, where I was headed was when you cap enrollment in computer science, you wind up with stealth computer science students sitting in other departments, taking your courses, wishing they were computer science students, and you get all the social.
Yeah,
backlash
absolutely,
from that.
absolutely.
But it seems to me that partnering with departments where those students are living.
Yep.
Which is more likely to be electrical engineering than English, would provide a better education for those students, better service for those departments, and less cross-departmental tension. Is it just that English doesn't want a computational English, or was that a?
They don't want the same thing at all. They don't want the same thing at all. Computer science at the University of Michigan teaches only in C++. We explicitly asked, no faculty member in LSA wants C++ for their research, not a single one. Right? Now, it totally makes sense for computer science in an engineering college to focus on C++. I get it. So I'm not trying to teach those things.
Why would it have to be in C++?
It doesn't have to, but let me, whoa, I forgot. This is way over here. That doesn't look like a computer science class to me. And let's not, one of the things that we do in computing education is we talk about CS0, CS1, CS2, which so implies a linear progression. There's no linear progression here. This is something completely different. It's the only thing that these critical computing people want for their students to know. They may never take a second CS class. That's okay, right? And then this one, the creative expression, this is what the computational artists want me to teach their students, right? It doesn't matter if they ever become software developers. That's not the goal. The goal is to give them the computing for their discipline. And I don't think computer science even wants this, and that's okay, because LSA does. Yeah, Carl.
I have a quick question about the courses that you taught so far at
Yeah.
the University of Michigan. Is it available online so that other people can just like grab the syllabi and the content to teach it at other places? Yeah, I don't know.
No. It is one of my goals for this summer. As you can imagine, I have been in quite a sprint for the last 9 months, and it just ended Tuesday and grades are due Saturday. So, no, I do not know. I do plan to make all of this stuff available. I just haven't had the cycles. Yeah, back here.
There are some questions on Zoom.
There's a question on Zoom. What do I do? Hit the chat?
Yeah, in the chat.
Okay, Ken, how are TSP languages similar and different from end-user programming languages or GUI-based developmental tools? I'm thinking of spreadsheets or PowerPoints or even styles or templates and word processing, or even more specialized tools like Josh's diagram authoring language or data analytic workflow authoring tool. Great question, of course. This is a question that came up in lunch. I am not trying to build a generalized tool. I do not have a teaspoon generator. I build all of these things by hand, me and my undergrads, because our top priority is to build exactly what they want in that discipline, so it looks like a tool for that discipline. That's our primary goal. So I don't think that's the goal of spreadsheets or PowerPoint. And I mean, it's one of the reasons why I'm using a term other than domain-specific language. Covering a domain, oh my God, that's nowhere near where I'm at. I'm good for one and only one task, which makes it super easy to learn. The UI is totally tuned to exactly that task. That's it. Speaking about English at Pitt, we are trying to engage students from English into computing using a joint major. I think that's great. But I think that there's also a space for computing in English that doesn't have anything to do with computer science.
The digital humanities and everything too. So.
Digital humanities, new media, lots of them. Yeah.
How do you think of the pedagogical affordances of the languages that you do create in the TSPs? Like, do they have commonalities in terms of how you sequence things or how you employ if they ever have a conditional concept? Do they look similar across TSPs? Like, because you're the one still designing all of the TSPs?
So that's a great one. You know, what's the Guzdial bias in each of these? I have no idea. Folks, please still make some other teaspoon languages so that we can compare, please. No, I don't explicitly try to have commonalities. For the most part, these teachers do not want computer science, right? So if there's any computer science there, I've got to be able to argue why you want that, why that has to be there. So like with pixel equations, it's really easy. This is the math teachers want to teach. I'm just putting it in boxes and making it executable. Nothing else is there. No curly braces, no assignment, nothing else. It's just the math you wanted to teach. I'm happy to apply it to image filters because you want to teach about robots and sensors. So that's been my path so far. Down the road, okay, here's the big picture. Is it more important to get every high school student to take a computer science course and probably learn a good general purpose Turing complete programming language? Or is it better to get everybody to try a dozen little tiny languages? Does the sum of all the little tiny languages across K through 12 turn out to more because you actually had to transfer, because you had to generalize? I don't know, but that's the sort of thing I'd like to be able to explore. Where are we at, Josh? Can we keep going?
Yeah, you keep going for sure. I didn't mean to signal you anything.
Okay, back row. Yeah.
So this jumps right off of what you just said. I teach the Introduction to Computer Systems course here, which is a very narrow sense computer science course, but we get a lot of non-majors taking it. And often those people come up to me like a semester later and like, I want to thank you for the class because the computer is no longer a black box to me.
Yep.
And so my question is, where does it's teaching people that it's not a black box fit into this vision?
Absolutely fascinating. Could I get a hum? How many people are currently reviewing for ICER? Okay, so oh crap. Okay. I'll signal when you can come back in.
I'll go get him.
We currently have a paper under review where one of the findings is that a whole bunch of the students at the end of the semester say, I want to learn textual programming languages now. Why didn't you teach me textual languages in the first place? I can also show you on day one, you said, Please, I'm so scared of textual languages. Really fascinating. Last semester, who took these classes? They weren't Comp 4, they were special topics that counted nothing toward. It's people who wanted that title. Computing for Creative Expression. The title alone attracted them. Every single one of them had tried to learn programming in the past and failed. What a fascinating group of subjects. So that's what we studied. They'd all failed. They all became successful. A bunch of them said, I would like something more, which is the right place for us to stop. Right? So yes, I think we are explaining something what's inside. So like the idea that pictures are made out of pixels with red, green, and blue, totally blew them away. That sounds are an array of values between positive and negative maximum volume. Wow. So yes, they are getting some of that and they like some of that. But more of it is about things like, why doesn't Alexa speak Spanglish? Well, let's talk about how sentence generation and recognition might work. You can come back. Yes.
So I really appreciate your talk. I want to push back gently a little bit.
Please, go for it.
So you kind of framed it as like the exploration of knowledge and the grubby factory turning out knowledge worker for FANG companies.
Oh,
Is the
I hope I
dichotomy
didn't do
here.
that.
And I'm not at all saying we need to be running a charity for FANG companies. But another way to frame this challenge is that I interact with a lot of people in my life who don't have a computer science degree, right? I have an accountant, I have a financial advisor, I go to the dentist, all these people, and almost all these people are using computing for their jobs.
Yep.
And so you said specifically you're not trying to get people job training or something like this. And I think I'm assuming
I want them to have the job that they were going to in English, public policy, history, whatever they were going for in the first place. I want to help them get there. I'm just going to give them some computing along the way.
So do you think that these teaspoon languages are going to set people up for the non-CS programming types of jobs that are heavily reliant on computational tools like Excel and, those sorts of things? How do you feel about that kind of pipeline from knowledge to making sure my accountant knows enough to not mess up my money?
Yeah, it's a great question. The job of that is the job of the people within those disciplines. The English faculty who are trying to produce the best English majors to get whatever job English majors get. And LSA has actually done an amazing amount of study of where do English majors go, where do history majors go, where do public policy majors go, and so on. I love this quote, right? I think this is a great definition. If you look at what we actually teach in most computer science programs, it is a subset of this. A very valuable subset. You get 6 figures for it. It's super. Lots of people should do it. But there's also something outside. I want to figure out how to teach that other part. Right? And that's about getting other jobs. And yes, we could do studies about, so what sort of computing does somebody need in English? But I don't have time to do that task analysis. Instead, I ask the English faculty. One of the things that are really pretty amazing, outside of computer science, people use computers. They program, a lot of them. Ask them, they'll tell you all about it. That's what I've been learning. Sam.
I'm not sure how to phrase this. It's probably a naive question, but how do you think about the balance between directed and diffuse learning in this field? So I feel like I had this idea in my mind of Scratch or Snap or other things as a stepping stone. And throughout your talk, I think I realized that's kind of a poor way to think about it because we're not trying to get people we're not trying to get everyone to do a CS job.
Yep.
But there's the things that Michael was talking about of teaching people the kind of computing that they need for the jobs that they are going to do.
Yeah.
And then there's the stuff that you're doing in your classes as well, which is the image thing of here's a cool visualization tool. Here's how to make art with computing.
Yep.
These are kinds of diffuse things that teach people concepts that make the computer not a black box.
Yep.
And because it's diffuse, maybe it will build up kind of foundational knowledge that you could use later when you're doing something directed. But how do you balance between teaching people specific skills and teaching people general concepts that are engaging that they can then build skills on later?
It's a great question. You're asking a big meta question that I don't know if Ken is still listening, but I'm expecting him to beat me up on tomorrow morning. Where's the transfer, folks? Okay, I mean, it's sort of implicit in Andy's question too. Are you teaching things so they'll be able to learn ifs later? Okay, I'm now going completely out on a limb. It's based on data that we've collected, but haven't published, haven't even finished analyzed yet. I think we've been thinking about transfer wrong. When we look at transfer between programming languages, we tend to look at the levels of structure and semantics. in the design community, they talk about one way of looking at design knowledge is in terms of structure, behavior, and function. Structure is the pieces that are there. Behavior is how the pieces interact. Function is why you're doing that in the first place. I think I'm seeing transfer at the functional level. People do things in pixel equations, and then they get to snap and say, oh, okay, well, if I want to do negation, I got to use this 255 stuff. Right? They're fuzzy on the syntax and the behavior, but they know exactly where they're going. They know the functionality, and the functionality drives trying to get transfer at the structure and behavior. I think our first goal is to get them to say, sort of like, I now know about how pixels work, right? I can't, not here, but at Georgia Tech when I was teaching media computation, which is similar, but at Python level, students would say, I now have a sense of how Photoshop works. I never thought of that before. Yes, and that transfer is not at the level of structure, not at the level of behavior, it's a functional transfer. That's where I think that we need to be looking for. Are you giving me a question from the?
Yeah, there's one more question on this.
Can you go ahead and read it to me, please?
Yeah. So, do you think that focused dual majors could engage non-CS students into computing much deeper than a more generic one-for-all approach? Of course, it is not either or. Both approaches could coexist.
Yeah, the question about what would get people interested in computer science is a terrific one, and somebody should ask that question. It's not my question. My question is, how do I help people get the computing education they need for the majors and the career paths that they're currently on? It's a great question. I don't have a whole lot of insight. Yes, ma'am.
This actually builds on that question.
Mhm.
I grew up with these guys.
Yeah.
I'm having some dissonance in the way that you talk about computer science.
Okay.
Because when you talk about computer science, you almost immediately transition to programming.
Yep.
And I get that dissonance because I grew up with these guys.
Yep.
So is it possible that this is setting up for you a separation and attention that you don't need, that you're creating an other where if you work within this frame of computing,
Yep.
You could be saying, it's not just about programming, there's also all this data, and learning to live with the data and infer
Absolutely.
things from the data is important. There are transformations,
Yep.
like, and this is going to lead you to parsing, which is going to lead you to programming, but you think about it as
Yep.
in a different way. Is it possible that if you took the broader view of computer science, that you would have less of a dichotomy in between the computer scientists and the people you're trying to reach?
Let me leave that one off the table. Let me just address the programming and the rest of computing one. CCAS will not just be about programming, but it will be about programming. So the new course that we're building, we're actually calling it COM4 101, how the transistor disruption, how a tiny tool transforms society and science. We'll probably have little tiny bits of programming, but not at all important. It's mostly going to be about what's a transistor and how did it change things, and Moore's law and all of that. All of those things that we know is how the transistor has changed things. I'm starting from programming because that's the big empty gap in arts and humanities. That they'd like students to be able to pick up programming in the junior and senior year, but nobody teaches it the freshman year. Let me just one step further.
They say they want programming, but that's the word that they have for.
They actually do use programming. When I first started showing one of the humanities faculty what I was doing, she says, but I want students to learn Unity. I require Unity. Like, okay, I'm not going to take somebody from I'm afraid of math to Unity in one semester. I can take you from I'm afraid of math to, well, textual languages aren't so bad. I'd like to learn some more about them. That's where I'm at. I'm trying to plug holes right now. I totally agree with you that computing, especially this delta that I'm describing, is way bigger than just programming. I'll give you the next course that I want to build. I have now met with both economics and political science. I meet with so many people and say, so what do you want about computing in your discipline? What do you want your students to know? And both of them say, simulations are what a lot of our research is built on. And I say, great, where do your students learn simulations? Well, the graduate level, what do you have at the undergraduate level? Zero. There is not a single course I can find on simulations in the social sciences at the University of Michigan. That will probably have some programming in it. It won't be C++, but it will have some programming in order to define discrete event, agent-based, continuous, a whole bunch of different kinds of simulation models. We'll probably do a lot of things like Nikki Case has been building. That's the direction I want to go. I'm trying to plug holes, and programming is one of the big things in that hole. People are scared of programming. Oh, we have so much data on how scared students are of programming. I'm trying to get past that. There's lots of else up there. I'm just me. This is where I'm starting right now.
So the way you introduced the application of languages here was focusing a bit on Scratch and how we have millions of Scratch programmers who have less than one project. Then one of the benefits of Teaspoon languages is that you don't have to amortize the cost. It's something that you can use once for a particular concept. So if I'm thinking about like a class where I'm teaching Scratch versus a class where you'd be moving through multiple Teaspoon languages, in both of those situations, I could see a scenario where someone exits class and doesn't necessarily use those tools again.
Sure.
So do you feel like the main benefit is the transition between multiple different ways of expression over just using one there?
It's a great question. I don't know. Explicitly, I'm not imagining any of my history teachers that I'm working with use more than one Teaspoon language, right? But I mean, how much do you remember of your K through 12? Some, not a lot. What if in high school, in 2 or 3 of your classes at each grade level, you used a Teaspoon language? Would that influence the way you think about computing? And if we explicitly, this is one of the things that we were just kind of blown away by. One of the tasks that we do when we do our interviews, Tamara Nelson Prom came up with this, is we show people, here's some C++ code, here's some Python code, here's some R, here's some Scratch. And the students come in, she had this happen 4 to 5 times. She can't tell me, I can't get all the details yet, the class I haven't turned in final grades, so I don't get to look at the transcripts. But she says, they came over and this, I've never programmed before. I don't know anything about programming. One time she's laying them down. The student said, but these are all, there's more than one programming language? I mean, we all laugh, but realize that most people don't know that, right? And then 4 or 5 times it happened when she laid down the R1, she said, oh, I've done that. I did that in Stats 250. But he called it programming, so they didn't know it was. And part of what I'm really intrigued by is that what if you taught a bunch of these Teaspoon languages across through to crowd and said explicitly, this is programming. This is the part that you might see in another programming language. Teaching for transfer. I don't know. I mean, I think it could have an effect, but this is an empirical experiment that will take a long time before we can test it. Yes, ma'am.
So I taught like mandatory freshman computer science. Or like, no,
Me too. We get commiserate. Yeah.
no, like I would love to talk to you afterwards actually about it. But what I found was that I thought one of the important things that I wanted to tell them was how good, like you know how people like, oh, if you play piano, you're really good at math or something. I don't know if you guys have
I've heard
heard
that
something
argument.
like
Yeah.
that, right? Okay, so what I felt was like these, I had these history majors and English majors having to mandatory take a computer science class and learn Python, right?
Yep.
And I thought what was really important for them to understand was how, even though they might never use it again for the rest of their life, but they could, was that it was like very good in helping them do like critical thinking, right? They learned like the processes, they learned how to, how to take like, stuff that they had no idea how to do it and then use that to solve problems, because it wasn't just enough that you're going to use a computer programming language, but it was like in life, there are a lot of times when you see these complicated technical tasks, maybe it's not called programming, but eventually they use that to solve problems. And I felt like that was something they would see in their jobs later on, regardless of what their major was.
Yeah. So I'm not sure I believe that. I think the evidence that you develop any sort of general problem solving skills from programming is very, very slight. But I do buy this argument that both CP Snow and Peter Naur are making. It's that far left of the learning trajectories. The idea that the computer code was written by somebody and they had goals and there's multiple programming languages and they all have to deal with this intermediate representation and bugs can occur all the time. I want everybody to know that kind of thing. And that does transfer, right? Because it's about what Peter Naur was talking about. Computing should be controlled by democratic processes. Everybody should be able to say, wait a minute, what if it went wrong? And these are the ways that I can imagine it might go wrong. How are you protecting me from that? I want everybody to be able to make those sorts of arguments.
One more question.
Yeah, over here then.
So I think like this is definitely a mixture of a lot of things. I think that's like really cool. But like one of the benefits maybe of having them separate is that you reduce the amount of like pedagogical content knowledge that the teacher requires in order to actually work through this. Do you think that this actually is going to make it so that if you want to do this, those teachers need to be better? Because they've got to have, not a mastery, but they've got to have a lot more
Yeah.
content knowledge on both sides. You know, are they making a history mistake or are they making a coding mistake?
Yeah,
As we talk through these.
it's a really good point. That is why, I'm trying to get to the picture of D.B. Farrell. This was designed in collaboration with teachers. With the way we describe it, our CICMP is, Tammy is our co-designer. Nothing happens in the classroom unless Tammy has okayed it. All the teachers who use our tools are design informants. I don't like this, I like this. Okay, in general, this is probably a change that we ought to make. I don't want it to look like computer science. There's no text editor there. I want it to look like history. There is going to be a little bit more ECK, a little bit more content knowledge. I am expanding the content knowledge requirements a little bit, but compared to a lot of other computational thinking in the discipline stuff, I'm not teaching loops and variables and conditionals. I'm trying to make it look as much like history as possible so that could be as easily adopted as possible. But even then, we had the discussion earlier about Perlis. I could give a whole other hour talk about the challenges of adoption. Adoption is really hard and complicated.
Thank you, Mark.